Bismillahirrahmanirrahim. Dear students of mathematical techniques for boundary value problems, MS Mathematics first and third semester. Today we will start our first online lecture. As you know that in our previous lectures we are studying the solution of ordinary differential equation with the help of perturbation techniques, and we have started an example of a singular perturbation for ordinary differential equation. In today's lecture, we will continue our previous example and try to learn how we can find the solution in case of a singular perturbation for ordinary differential equation. We are solving this example, which is the oscillation of a mass connected to a nonlinear spring, and this phenomena was described by the Duffing equation x double dot plus k square x plus epsilon x cube equal to 0, and we have two initial conditions: x of 0 is 0 and x dot of 0 is ka, where epsilon is a small positive number. We have already done all these calculations in our previous works, that we assume an approximate solution in a regular perturbation way given by equation number 2, that is x is equal to x naught of t plus epsilon x1 of t plus epsilon power 2 x2 of t up to so on. Now putting equation number 2 in equation number 1 and equating the coefficients of like powers of epsilon, you know that we have three systems. Number 1, for epsilon power 0, that is a constant, the differential equation is x naught double dot plus k square x naught equal to 0, and the two initial conditions are given by equation number 3. Similarly, equating the coefficients of epsilon power 1, we get second system, which is x1 double dot plus k square x1 is equal to minus x naught cube, and the two initial conditions. And the third system is by equating the coefficients of epsilon power 2, and we get the system given in equation number 5, which is highlighted over here. After equating these systems, we have to find the solution of these three systems: equation number 3, equation number 4, and equation number 5. So the general solution, which we have already computed in equation for equation 3, is a1 cos kt plus a2 sin kt. Using the condition x naught of 0 is 0, we get a1 0. So our solution x naught will be equal to a2 sin kt. Now using the second condition x naught of dot is of 0 is equal to ka, we get a2 is equal to a. Therefore our solution for x naught, which we have already computed, takes the form given in equation number 6 and highlighted over here. X naught is equal to a sin kt. Now we have to solve the system 5, that is we have to find the value of x1 of t. Now putting the value of x naught from equation number 6 into equation number 4, we obtained x1 double dot plus k square x1 is equal to minus a cube sine cube kt. Now using the value of sine cube theta, which is 3 by 4 sine theta minus 1 by 4 sine 3 theta, the above second order ordinary differential equation becomes as given in star and highlighted over here. Next, we have to find the solution of this system, which we have already obtained in our previous lectures. This solution x1 is given by equation number 7, which is highlighted over here. X1 takes the value minus a cube over 32 k square sine 3 kt plus 9 sine kt plus 3 a cube over 8 k t cos kt. Now we restrict ourselves to the two terms approximation, that is x naught plus epsilon x1. Therefore, the putting the value of x naught and x1 from equation 6 and 7, we get our required solution for this problem, which is given by equation number 8 and is highlighted over here. This is our required solution x for this second order initial value problem. As I told you earlier that the difficulty in this solution for us is the secular term, which is the third term with epsilon minus 12 k t cos kt. The coefficient which I have already written over here, that we note that the coefficient of epsilon, that is x1 of t, is not bounded for all t, because for t approaches to infinity this term is approaching towards infinity. The term t cos kt is called a secular term. Such type of term is known as the secular term, and this propagates itself to higher order terms in the perturbation expansion, so that none of the xk's is bounded for all t, and as a result no approximate solution can be obtained through truncation of the series, that is perturbation breaks down, because by larger values of t this term is unbounded, and when we compute in other terms in our approximate solution, then this is propagating itself, and therefore as a result the approximate solution cannot be obtained by truncation of the series. So this is the main cause of difficulty for singular problems, singular perturbation in case of ordinary differential equation, that is we obtained a secular term. At the start हमें नहीं पता था, but when we proceed according to the regular perturbation method, and as a result at a we come with a secular term, which is the cause of difficulty for us. So the main topic starts from here, that how to get rid of this or these secular terms, and how we can obtain a regular perturbation expansions, and the answer is, to cope up with such a situation we use a different technique, which is known as straining method. So whenever in a ordinary differential equation, we get in the solution of an ordinary differential equation, we get a secular terms. Then we will use the method of straining coordinates or straining methods, and these consist in their simplest form of applying perturbation expansion on both the independent and dependent variable. So the important step of the straining method is that we have to apply the perturbation expansions both on independent variable and डिपेंडेंट वेरिएबल. इससे पहले हमने क्या किया कि हमने जो ये एक्सपेंशंस थी वो सिर्फ और सिर्फ डिपेंडेंट वेरिएबल पे हम अप्लाई करते रहे और इंडिपेंडेंट वेरिएबल को हमने ऐसे ही छोड़े रखा. लेकिन अब हम क्या करेंगे कि हम डिपेंडेंट वेरिएबल के साथ साथ इंडिपेंडेंट वेरिएबल पे भी इस एक्सपेंशन को अप्लाई करेंगे. वो कैसे? Our dependent variable was x and our independent variable was t. So we have introduced a new variable in for time, which is tau, and perturb the independent variable t in this form of equation, in this form given in equation number 9. That is, t is equal to tau plus epsilon f1 of tau plus epsilon square f2 of tau. This is the most general form of the perturbation expansion on the independent variable. Anyhow, the dependent variable will be this will be expanded in this form given in equation number 10 x of tau. अब हमारे पास जो डिपेंडेंट वेरिएबल है वो t की जगह tau में चला गया because time has been changed to tau. So this expansion is of the form x naught of tau plus epsilon x1 of tau up to so on. So the straining method is simply consisting of these two equations 9 and 10. That is, we have to introduce a perturbation expansion for both independent as well as the dependent variable. And one thing which you have to notice that with fi of 0 is equal to 0, that is all the functions fi's in equation number 9 are 0 at tau equal to 0, because so that t equal to 0 will correspond to tau equal to 0. I told you that equation number 9 is the most general form. However, in our problem, in our solution of the problem, equation 9 is replaced by equation number 11, which you can see over here, that in practical applications we will use the perturbation expansion for the independent variable t of the form 11, which is highlighted over here. That is, t is equal to tau into 1 plus epsilon b1 plus epsilon 2 b2 up to so on, where these constants b1 b2 up to so on bi's are the constants to be determined so that the secular terms disappear from the perturbation expansion. So our another task in this problem is to find these constants bi's in such a way that the secular terms will be disappear from the perturbation expansions. तो अब हमारा काम जो है वो आप देख सकते हैं यहाँ से कि we have to apply the perturbation expansion on x of t, the dependent variable, which is given in equation number 10 over here. You can see I am highlighting it, that first we will apply the perturbation expansion as we have done earlier on the dependent variable, but the new thing in this method is that we also have to apply a perturbation expansion for the independent variable t in this form, which is given in equation number 11. So that's end of this lecture, and I will continue the next lecture from the same lines and from the same page, page 23 and equation number 11. Thank you very much.